everyone, this is Professor Jeff Wilkerson with the introduction to our first laboratory project for Physics 182 in the spring of 2021. Off and running we are. And we're going to try to measure the index of refraction of a glass block. And we're going to try to figure out if we can determine whether the index of refraction is different for green light and blue light and purple light. And we're going to go about trying to measure these indices, and we need to measure them as precisely as we can, because if they are different from one another, that difference is relatively small in terms of a percentage of the value. And so that's one of the things we want to work on in this lab. It's not just saying, well, something's big or something's small, because it doesn't have any absolute meaning typically. But we will be able to say, relative to the overall value, the difference might be small or something like that. And so we got to be very precise about how we're going to try to measure this. So the index of refraction is usually given the symbol N, and it is a measure of the speed of light in vacuum divided by the speed of light in the material. Okay, so that's our starting point, is to say the speed of light in vacuum is always greater than the speed of light in material. We'll say always for the purposes of this class, and so n is greater than or equal to 1. Okay. And so we're looking for something that's bigger than 1, and we're going to try to measure that index of refraction. And in order to do that, we're going to take as a given. Now, we should try to verify this, but we don't have time to verify everything in the lab. So we're going to take as a given Snell's law. And so Snell's law tells us that the index of refraction of this medium. So this is a medium. It's going to be a glass block for you. So that's your glass block, but it could be any other. It could be water. It could be air. It could be something else. It could be, and we're going to have air out here. And we're going to take the index of refraction of air to be the same as the index of refraction of a vacuum. Okay? So we're going to take air to be N equals 1.000. Okay? So we're going to take that to be our index of refraction of air. And we're going to try to find out what the N of glass is. And we're going to try to do this for several different colors of laser light that we have incident on this glass. So what happens? What Snell's law tells us is, if we draw a line that's perpendicular to the face of that glass, then we have the laser come in, the light come in this direction. Let's have it come in this direction. Okay, and it strikes the glass right there. You've got some theta, and we're going to call that theta incident. Okay? And then it undergoes refraction. If N of the glass is greater than N of the air, it's going to be refracted. It's going to be bent toward the normal, toward this line that passes through the glass. Okay? And so it's going to go through here, and that's going to be theta refraction. Okay? So, or the theta transmitted, if you will. Let's call it theta t for this class. So we're going to call that the transmission angle right there. Theta t. Okay? Snell's law tells us that N of the incident material times sine of theta of the incident angle times the sine of the incident angle is equal to nt sine theta t. Okay? Great. So now we can solve this for the index of refraction. Your task is try to figure out how to do this experiment best, so we get this in as precisely as we can. And there's sort of two components to that. One is you've got to do this. You've got to set everything else up right. You know, one of the ways I would go about doing this, if I were doing this experiment, is I would probably just have the light come in this way, measure that angle, and then maybe determine this angle right here by measuring what that thickness is and what that distance is right there. How far to the right of that incident spot did the laser come out? And if I know that distance and I know that distance, I should be able to get that angle pretty well, right? I know my trigonometry, and I can do my trigonometry to dig that angle out without any problem at all. Okay, so that's going to be one of the ways you could go about doing this. But you have other ways you might, and you should think about what those ways are. But that falls apart if this block is askew, right? If this block isn't perfectly perpendicular to that line that you think is right here. So you got to figure out a way to try to make that block perfectly perpendicular to that line. And it's going to matter more depending on if it's not perpendicular or other things. And the other thing you're going to find is the spot size of these lasers isn't great. Okay, you're going to look at it and say, oh my goodness, the spot size is really thick, and you got to make some kind of estimate of the middle of that spot size or something right there. All of these effects might matter more at very small angles of incident than they do at very large angles, or they might matter more at large and small than they do in the middle. So you're going to go, I'm going to recommend that you go and try it in a whole bunch of angles and see what you can do. Now, you might try it this direction, and then move the laser this direction and try it this way and say, if this isn't exactly perpendicular, maybe that effect cancels out by going these two different directions. And you can look at 45 degrees this way and compare it to 45 degrees this way, or average those two out, or something along those lines. And so you want to try to figure out a range of values, angle values here, that seem to give you the cleanest incident index of refraction measurement. Okay, so we looked in one of the previous videos. So one of the things you could do is you could plot index of refraction as a function of theta incident and see, is it scattered all over the place? Scattered all over the place. How does it work? Where's my best data? And then you go hard at the data in that region, and you need a lot of points. The more points you have, you talked about this in Physics 181, I think, is to say, n, you're going to take your n to be the average, the mean of a whole bunch of values that you take, plus or minus the standard deviation of those points divided by the square root of n, what we would call the standard error, okay? So that's your uncertainty that you're going to have in your data. And we're going to talk about how to turn those uncertainties in the next couple of weeks. We'll talk about how to turn those uncertainties into percentage likelihoods of being in a given range, or whatever that is. And so you're going to, but the more your n value is, that's not the same n, that's n, the number of trials. And the more your number of trials is, the smaller your uncertainty is, as long as you're doing everything else well and you don't have some big offset or something like that. So if you could get 10, great, 50, better, 100, super, 1,000, probably not, but that'd be fantastic. You're going to be in better shape. So you need a lot of data points, and you need them in a range where you don't have a lot of scatter in your data, or you don't have some kind of offset effect or something going on. And so that's your job, is to set up how to try to figure out this index of refraction. You'll use Matlab and Kaleidograph. I've put help files for those things, help links on the Katie site. You've been using Matlab, I know. Kaleidograph is on your machine too, and I encourage you to use both of those things to practice them and get better at them. And so you'll set up formulas in there to be able to turn one column of data into another column of data, and we'll figure out how to make the graphs that you need to make, and how to make histograms, and how to fit Gaussians. That's what we're going to take off and do, is fit Gaussians to histograms. So you want to get enough data points here that you can fit a Gaussian to those data points, and that Gaussian gives you meaningful results for the mean and the standard deviation. That'll be our introduction for next week, is how to do that. But that means you need as many points here as you can. 7 or 8 points ain't going to do it. You need data in 6 or 7 or 8 bins at least of data, and that data needs to be, you need enough data in each one of those bins to be able to tell meaningfully the difference between one bin and the next. And we're going to spend so much of this term working on that idea, on uncertainty in how much, what a bin value is, and uncertainty in the mean, and so on, as we look at these histograms. So we're really going to hammer that thing hard. But what you're going to do right now is, for this first week of this lab, it's going to be a 3-week lab, so you got 3 weeks to work on this. You got 3 different colors of laser, and you're going to think, wow, that's a lot of time. I should be able to do that easily, but you can't. It's very hard to get all of this and figure this out. And how good a job you do is going to determine whether you can tell the difference between index of refraction for red light and green light and blue light as you go through this. So this is it. This is the theory behind the idea of what we're trying to get done this week. You're going to try to measure the index of refraction of this glass block by measuring the incident angle and the transmission angle, and using Snell's law. Again, the incident angle is going to be 1, and so you can solve that for NT and figure this out, and we can go on along this direction. If you measure y and x like this, you can set up a formula in Matlab and or Kaleidograph to have it churn out all of the values for you of theta, and so you can turn out values of sine theta t that you want to stick in here and get this thing pushed through. So your first week here is you're really trying to figure this out. If you figure out a good range of angles to use, I'm going to say maybe take a shortcut, and in future weeks when you're using the other colors of lasers, you can assume that angle range is just as good and the same. But maybe that's not good enough, and maybe you need to retest that each week, and you might have somebody in your group doing that while somebody else is doing another thing. So you have people working on different aspects of this. They can be working on the data analysis and trying to analyze the data in a meaningful way that's going to help you feed back in here. Other people can be taking data over here and comparing data with the green laser compared to data with the purple laser and trying to figure out what's easy and what's hard to do and what's the best way to go about doing it. How to figure out how to contain the spot size of the laser so you can determine exactly where it's coming out right there with the best precision and so on. And then just getting lots and lots of data, you know. If you got 3 people and you got 3 setups, go after it. Everybody get 30 or 40 measurements in this day, and then 30 or 40 measurements next week, and 30 or 40 measurements the next week. And always stop. Don't just pull ahead. Always stop and look at the data and think. The best thing you can do, that's the single best thing you can do in the lab, is think. What is this data set telling me? What do I see in the data right here? And how do I make meaning of that to help me do what I need to do to get the value that I'm trying to find right here? So that's our job. We're going to try to find we're going to spend the next 3 weeks. We're going to spend the whole month of February basically trying to find the index of refraction of this block of glass for different colors of light, and really honing our experimental technique in order to figure this out. So thank you, everybody. We'll see you soon, and I'm looking forward to getting this lab underway.